Good morning, everyone. So, we leave the best till the end of the conference. So, it's my great pleasure to introduce to you Professor Alexander Yarin. He is the former professor of the Technion Israel Institute of Technology, but at the present he's distinguished professor at the University of Illinois, Chicago in USA. Professor Yarin is an author of 5 books, 12 book chapters, almost 450 research papers, and 12 patents. He is also fellow of many distinguished foundations. I will not read because the list is really long. And he's one of the 3 co-editors of the Springer book of experimental fluid mechanics, also associated editor in the few journals, let me say few names like Experiments in Fluids, in Advisory Board of Physics of Fluids. So, Alex, the floor is yours.
Thank you very much, Ulla, for your kind presentation. So, I'm Alex Yarin from the University of Illinois, Chicago. Here you can see the view from the campus, not from my office, but this is close to the downtown of Chicago. Now you are familiar with Chicago. It's like Poof Poof, Al Capone, you know, but we also have some very good blues clubs, you know, some best theaters, the Art Institute, so it's a pretty nice place. And we do work there. So let me start, you know, this talk about like several relatively recent, you know, developments in my lab and in several groups with whom I collaborate. And I'd like to start acknowledging them. Like, first of all, the Nonwoven Institute for the support, and then, you know, my collaborators who are, first of all, my students from my lab who are listed here, as well as some colleagues from all over the world. For example, Dr. Purdahimi from North Carolina State University, Sam Yoon from Korea University, and Professor Seon Pilan, who was my postdoc, and now he is a professor in Korea, a very long name of the university, and he's here in the audience. So if I'm wrong in something, he'll correct me. All right, so now that's an outcome. So I'll try to show you several, you know, efforts to introduce some additional physics to nanofibers and to filtration processes related to nanofibers. So essentially the focus is on like filtration or penetration of fluid, liquid or gas and particulates through nanofiber membranes, and what good could be achieved from using some additional, you know, physical phenomena. So I'll begin with the topic number 1, which is listed here. It's about like wettability. Essentially, is it possible to make a waterproof fabric, and if it's possible, what does it take, you know, if it's based on nanofibers? That's topic number 1. Topic number 2 I'll try to cover would be introduction of van der Waals and Coulombic forces in filtration processes. So what should be done to do that, and what benefits are expected? And topic number 3 is already like electrostatic forces, mostly in filtration on the macroscopic scale, what good can come from there, and what kind of like particulate pollutants and different pathogens can be stopped and incinerated using this type of an approach. So let me start with the superhydrophobic Teflon glass Electrospun fibrous membranes. So glass was already mentioned yesterday by Professor de Klerk in her work, so it looks like it becomes a popular topic, introduction of glass in nanofibers. So that's what we have tried to do. So we organized electrospinning of a blend of essentially Teflon, a little bit of PO for spinability, and glass particles. Now, the idea is to make ultimately, fibers which are super hydrophobic. This is number one, and also to enhance the super hydrophobicity not only by the chemical, nature of Teflon, but also by roughness introduced by glass beads which are inside. So when you do this type of electrospinning, so after all, you end up with fibers which you can try to sinter. And when you sinter them, so you eliminate PO completely, which is unneeded. It's just like a plastifier, essentially, during the process. Whereas you sinter glass beads, and you have Teflon covering everything, and the beads providing roughness. So the idea, as I told you, is waterproofness, and I'll show, and some other additional properties, and I'll tell you this step by step. So this is an overall, approach which starts with electrospinning and goes that way. So what kind of fibers do you get? Depending on composition, you might have, fibers which are pretty ugly, fibers which are less ugly, but still, the beads are outside, so it's a disordered structure. But after all, you can, end up with fibers which are pretty ordered, and they are, after sintering, are fully Teflon, and sintered beads provide a lot of roughness on the local level, so a lot of surface area as well. So this is essentially the type of fibers I'm going to talk about. Now, these are some characteristics of this type of membranes, and we addressed also their porosity, how porous they are, and their roughness and their thickness, okay? Because I'll show you that essentially waterproofness is mostly about thickness and not at all about non-wettability of Teflon or roughness of the surface, okay? And this is a less understood, issue which I want to ascertain. So this is an information about porosity depending on the thickness of the fibers and morphology. So I'll skip this over. This is one additional slide which shows the pore size as a result of the thickness, and essentially the thickness increases and the pore size decreases. Okay, so the dependency is highly nonlinear, and the process essentially goes as mostly filling the pores when depositing additional fibers, so you diminish the pore size. So you end up essentially with pores on the scale of several microns, which is typical for electrospinning, and thickness can vary, and we vary up to essentially 100 micron. Now, wettability characterization. So these are I'll skip over multiple details listed here, but also only concentrate on this pictogram, which shows you what kind of droplet configuration, water droplet configuration you might expect on this type of nanofibers. So essentially you can see that in many cases you have the contact angle, the apparent contact angle of about 150 degrees. So this is indeed a highly super hydrophobic material by all definitions. And the question is it enough to prevent liquid droplets, from perforation through this type of nanofiber mats? There is also some information about stress-strain behavior. So you can see that this is essentially initially elastic, then it's hyperelastic. This is stress-strain curve, so it's hyperelastic part, and then in some cases you have a long plastic branch, and in some cases, the fibers become stiffer, and you have, an abrupt catastrophic breakup in stretching. But all in all, these are pretty robust, fibers which we made, and I'll show you some additional tests of these fibers, not only in stretching, but also in abrasive, action and chemical aggressive, media and things like that. So now let's come to like the applications essentially. Okay, so electrospinning is essentially a tool to make some protective layers in my mind in this work, and we wanted to test how do this superhydrophobic nanofiber membrane protect from penetration of water through them. And water essentially comes, in many cases as just rain, so that's a kind of like a rainy experiment you can organize. It's a very simple one. You drip droplets, from different heights, so that regulates, viscosity, velocity of impact, and you can easily start from 1 meter per second and reach, 5 meters per second, and this covers the entire range of droplets in rain. So that's exactly the range of interest. Now, the membrane by itself is supported by a stiffer something, as usual, it's usually done, but the stiffer support has much wider pores, so for filtration purposes, so like penetration purposes, it means nothing. So the support is just mechanical, not to break the membrane, when a droplet impacts it. And the main hydraulic resistance is coming from the very thin layer of nanofibers which we made on top. So this is the experiment, and this experiment allows us to observe, penetration directly through CCD camera recording. So okay, so let's begin, with a relatively low velocity of impact, something like 1 meter per second, and here you see some images like taken during the impact, the impact phenomena observed in such cases, like low velocity impact. So you see a droplet coming to the membrane, spreads over the membrane, and then recedes and produces the so-called Washington jet, which essentially disconnects or tries to disconnect partially or fully from the surface. So this is a very good outcome. This is exactly like a protective action of the membrane. This water droplet cannot penetrate the membrane. So then, a different experiment shows you essentially, not a different, but a different time frame, shows you the continuation of that. So you see the Washington jet, which was bouncing back already, breaks up by capillary instability and a succession of droplets, and this is like a full protection. Okay, very good. But the problem here is that the velocity of impact is only 1 meter per second, and it's interesting to go higher. So let's take a look, what happens when you go higher. So these are a series of experiments where velocity is increasing. And the higher is the velocity of impact, and what I'm seeing here, I'm going not very high, essentially, like 2.3 meters per second. In this case, you already see quite a lot of penetration of water through this superhydrophobic membrane. Okay, so then it appears to be that essentially superhydrophobicity is a miracle, and a kind of like I would say not even a miracle, but a mirage. Okay, so you see that the water easily goes through Teflon membrane, with additional roughness, and you cannot stop it, when velocity is increased, to 2.3 meters per second. Okay, so we are interested in this part below the line. The line itself is a membrane, and below the line is essentially the portion of water droplet which penetrated through. So now you can manipulate also, like higher, you go to higher velocities and you see even more penetration. The penetration already takes shape of like merge, tiny jets going through pores, and a central jet appears like that, and more significant portion of the oncoming droplet is perforated, going through the membrane. By the way, it looks like that you essentially made a hole in the membrane, but there is nothing like a hole. So you can inspect these membranes after this type of penetration, and you'll find them absolutely intact. So all what is coming through is coming through the pores, and the membrane is absolutely undamaged. So then you can also start to increase, thickness, and when you increase thickness, so like intuitively it's clear that, you can diminish penetration of water through the membrane, and indeed it happens, like you see less and less water penetrates. You have a pretty chaotic phenomenon on the top when you go to higher velocities, but the main thing that you do you do protect, the lower part from water penetration. So these are competing factors here, like higher velocity, water goes easier, and higher thickness of the mat, water goes slower. But this is all a trade-off, because to what extent, the question is, to what extent can you increase, the mat thickness? Because there are some additional issues, like breathability, for example, is very important, because this is all about like something you put on the body, and we are going to explore breathability as well, and we'll see that there are limitations on the thickness. All right, so now this is like already a quantitative information of what happens here. So this is the volume fraction in percentage which penetrates, according to the impact velocity for mats of different thickness. And you see that you can easily reach, like almost like 100% penetration when your velocity goes to 3 meters per second. But increasing the thickness of the membrane, you can diminish this penetrating part less and less, and diminish it practically to zero. So this is already like an overall information which came from these experiments. Now the question is like, what is the physics responsible for water penetration through superhydrophobic membranes? And I'm going to skip over all the detailed calculations and show you only like the main result. So this is a problem which can be treated, as a planar problem. So essentially it's like a cylindrical, droplet falling on an infinite membrane, or it can be considered as an axisymmetric spherical droplet. So either way you can solve this problem analytically, and here there is the result. So V0 here is the velocity of drop approach. So that was 1 meter per second to 3 meters per second, what I discussed before. Now U here is the velocity of the original penetration of water into pores. And there is a factor, okay, the numerical factor in planar problem 4 over pi, it's of the order of 1, but there is a ratio of the droplet size, capital D, to the pore size, which is a lowercase d. And this ratio is on the scale of like 1 millimeter to 10 micrometers, okay? So the ratio is essentially like about 100, or sometimes it can go even to 1,000. So it means that even so you have 1 meter per second, the approach velocity, but water goes into pores, with velocity of the order of like 100 meters per second, okay? And this is a tremendous velocity, okay? So if you go like 1,000 meters per second, this is such a tremendous velocity. You're approaching like compressibility, like a sound speed of water. And if you compare this velocity with the so-called Laplace-Washburn speed, which is the velocity of penetration by wettability. For example, you have like a fully wettable membrane which sucks water in by wettability. Okay, so this result describes, how fast this suction goes. This is a kind of like a diffusion process, and this result essentially relates, the penetration with it stands surface tension, because surface tension is equal in this case, to the other surface tension, which is pulling inter, okay, liquid to solid surface tension, but it's equal to the liquid gas surface tension, so it's a misleading factor standing here, but I'm explaining why it's like that, okay, and also inversely proportional to viscosity of penetrating fluid, and obviously the thickness of the mat. So after all, you know, the Lucas-Washburn speed is very, very small compared to this velocity u you predict here. So it means that, you know, when you have drop impact on a droplet which is much larger than the pore size, so what happens here is a phenomenon of, as we called it, hydrodynamic focusing. So this is a phenomenon where you bring a kinetic energy and suddenly you let it go only through very small outlet, okay? And this kinetic energy, even so not huge originally, okay? But when you focus it into tiny droplets or a tiny pore or several tiny pores, okay? So it becomes a tremendous, you know, speed. Now, therefore, wettability plays no role at all, and all these efforts essentially to make it like Teflon or not Teflon, it doesn't matter, okay? You wish Teflon, okay, this is done. But still you go through Teflon, obviously. All right, so the axisymmetric case is the same, so only the factor changes. So that's the physics. Now, the details of calculations of this type you can find and some additional experiments in my book, you know, published by Cambridge University Press, so this is just like information. I'll skip the details over, but I'll show you a detailed measurement, you know, how it goes. So this is a membrane, a droplet impacts the membrane, and you can observe, you know, individual jets coming below the membrane. And by the way, this is special fluid, you know, which is called FC75, so these are fluorinated fluids, you know, which have low surface tension. So then, you know, you don't have merger of these individual droplets here into individual jets into central jet, and you can observe individual jets coming from the membrane, and that's the main point for using this fluid. So what you can do then, you can measure the velocity of these ejected jets, you know, coming after the membrane, and the result is puzzling. You know, the impact velocity here is 2.1 meters per second, whereas the outflow velocity is 3 times higher than that, 3 times higher. And this is all after all these viscous losses flow in tiny pores, okay? And that's exactly what I told you. This is a hydrodynamic focusing, okay? So this is a direct proof, you know, that it exists, and that's how it works. So then, you know, the question is, all right, okay, so if you cannot stop by wettability, non-wettability, roughness, so what about like the effect of thickness? Yeah, indeed, you know, you can easily calculate, you know, I'm skipping the calculation over, that there is always a critical thickness, you know, which is exactly the thickness where all this kinetic energy will dissipate by viscous forces, and there won't be any outflow from the membrane. So we tried, you know, to compare this simple prediction with experimental data, and okay, the theory is very like simplified here, imperfect, but all in all, you know, what you see here, like first of all, porosity, roughness definitely is helpful, and for a certain value of roughness, so our prediction goes this way. So this is essentially the critical thickness which stops penetration for different velocities in the range of water droplets. So the prediction goes this way, the experimental data goes this way. Okay, the agreement is definitely not great, but at least, you know, the trend is caught, and this shows, yes, that you can, you know, like make something waterproofed, you know, but the thickness should be high enough, and the thickness should be about like from like 10 to 50 micron of this type of fibers, you know, to protect against rain, for example. Now, all right, now let's go to some other things, you know, like breathability. So breathability is a very important thing, you know, because like you need to remove vapor through membranes, you know, if your body is inside, otherwise you cannot, you know, sustain it. So I'll skip over all these elementary definitions of like what is breathability and just show you how the experiment works. So here we put, first of all, like a certain gas, you know, which can change color of droplets, you know, with a certain marker, okay? And this is our membrane. So the gas is trapped inside the beaker here, the membrane sits here, and you put different colorful droplets on top, and if the membrane is breathable, so then the color changes, and that's what you see here, okay? So these membranes are not only like thick enough, not only waterproof, but also breathable. That's already a good point. Now another experiment related to breathability is like that. You fill a column, with a liquid and put the membrane underneath, okay? And this membrane underneath essentially is also connected to a reservoir filled with liquid or with gas, which is, for example, air, okay? Then, the membrane appears to be holds, the entire column of liquid, so liquid is not leaking through. However, bubbles are going through the membrane, so it means that it's breathable for gas and fully impenetrable by liquid. So this is also like an experiment, which convinces that there are some good properties of this type of membranes. So I'll probably skip over this is repetitive, information, and now I'll come here. So the question is, all right, you put such a membrane, on top of like larger substrate with larger pores, like which is just a mechanical support. But to what extent, it's like mechanically stable? So we did experiments of this type. So abrasive like action imposed on this membrane. So you essentially not only like rub it, but also you put like a significant, weight, like 100 grams, for example. So you apply a significant like pushing force and you rub the membrane. So when you observe the ICM images, so you see that, some fibers are definitely damaged, okay? But nevertheless, the membrane doesn't lose its properties, okay? For example, like its superhydrophobicity survives after all, several cycles of like rubbing like that, so it withstands the abrasive action. This is also a good point. Now, now self-falling, and self-cleaning. Now, you expect that, okay, if you are not interested in only like droplet penetration, so the question is, if you'll tilt this membrane, so can it clean itself, just by tilting? And that's what we do here. So we put droplets on top, we tilt, and these droplets roll over. That's okay. So it's a pretty like superhydrophobic behavior. Okay, no significant so-called hysteresis. Now another question is like if you put charcoal on top of it, can you remove it? So because these are already adhesive particles, so can you remove them easily? And it appears to be that just by directing, a small water jet, you can easily clean everything. So the jet is here, colored by blue color, just to see, where this water used for cleaning, and where is charcoal removed from the surface, and the surface which was fully covered by this charcoal is now white once again. So like a Teflon surface. So this membrane, has some additional, positive properties, and I'd like to ascertain them. All right, so these are my conclusions. I already listed this. So if you are about penetration, so then make it thick enough if you can allow yourself. Otherwise, it's also withstand abrasive, action. I skipped over, some alkaline chemical action, which also doesn't affect the membrane, and it can also be very breathable. So that's my first topic. Let me switch to another topic, van der Waals and electrostatic forces in filtration. So van der Waals forces are well-known forces, but the problem with these forces is that they act only like at the range of like 100 microns. So if you are beyond 100 microns, so van der Waals forces are ineffective. So if you have a filtration, if you have a collector like that, and the particulates are coming, so if a particulate is moving more or less like closer than 100 microns, it can experience van der Waals forces, okay? But if it moves above that, you know, you cannot experience, it doesn't feel. So then the question is, can we make, you know, fibers which are small enough not to displace, you know, flow to that extent, you know, that you lose van der Waals action, okay? Then you'll be able to benefit from van der Waals action. And here we introduced once, you know, for other purposes together with Dr. Yun from Korea University, the so-called supersonic solution blowing. But essentially, the supersonic solution blowing begins with electrospinning. So you have like an electrospinning setup, a jet, you know, which is issued, I believe, from here. It's too small for me. I'll probably go to the next, you know, sketch. So essentially, here you have like electrospinning jet is coming, okay, and here you have the so-called Laval nozzle. Laval nozzle is essentially like a type of nozzle, convergent divergent nozzle, which allows you to organize supersonic gas flow. So this is the main tool, you know, which organizes propulsion of like aircraft, jet fighters, typically ballistic missiles, you know, things like that. But in our case, this Laval nozzle is one of the electrodes, so it's also included in the, it's a grounded electrode, and another is electrospinning. So essentially you begin with electrospinning, and electrospinning makes a jet already pretty thin, you know, through bending, but this jet, you know, bending jet is also attracted to the Laval nozzle, and the Laval nozzle is blowing supersonic gas flow, so let's say 500 meters per second, something like that. And then, you know, the jet is entrained by this, the polymeric jet is entrained by the gas jet and strongly stretched once again with bending instability already of aerodynamic, like flak, you know, flapping action, and deposited here as very tiny fibers. So this is the way how to make nanofibers in the range of like 20 to 50 nanometers, okay? And that's already an interesting range for us. But, okay, 20 to 50, that's like the record number, but below 100, that's what we want to do. And below 100, you want to make on demand, okay? Not by chance, you know, sometimes you have in electrospinning, but on demand. So you might think that this is something bombastic. I mentioned jet fighters, you know, ballistic. Okay, even so, it's a very popular tool today. But nevertheless, you know, this sounds bombastic, but essentially it's not bombastic. This is a Laval nozzle we use in the lab, you know, and this is something like that. So you can have a mini scale Laval nozzle and still, you know, measure velocities like 5 meters per second. All right, so then, you know, the deposited fibers are illustrated here. So this is a surface, aluminum surface without any deposition, and this is already covered by the supersonically blown nanofibers, and these are on the range of 20 to 50 nanometers. So this looks very different from a regular electrospun mat, because it's very transparent, very milky. It's very different. So you see the surface through. And nevertheless, you know, it's fully covered by these fibers. Now, we did some filtration experiments. So in this case was filtration through liquid. I give some references here, so if people are interested, you can see more details here. So essentially, you know, what we did, you know, we took like the basic commercial filter, okay, with essentially was, I believe it's cellulose or something like a trivial commercial, you know, with big cells, about like 50 micron. On top of that, we deposited just regular electrospun nanofibers, and then on top of that, we deposited a layer of like supersonically blown nanofibers. So on this ICM, you see all the structure all together. So some big fibers in the background, this is like the supporting filter, okay? Then you see electrospun nanofibers, which are intermediate in size, okay? And then you see the thinnest ones, you know, the closest to you. These are supersonically blown, like 20 to 50 nanometers. So, and then, you know, we did some filtration experiments. So, like the basic filter, okay, glass fibers, okay, I said cellulose, glass fibers. the basics, then glass fibers with Electrospun, and with supersonically blown. So I'll concentrate on that. So interesting that, you have collection of nanoparticles. In this case, nanoparticles were like copper particles, just for our detection purposes. It's easier to use copper particles on the scale of like 100 nanometers. This is a very difficult scale to catch because neither diffusion nor inertial effects, are effective in filtration. And what you see here is that most of the collected clusters are hanging on the thinnest fibers, okay? So the thinnest. So you might expect that, the bigger fiber you put, the better you intercept. But it appears to be just the opposite, okay? The thinnest fibers are the most important collectors. And I'll give you, okay, this is some additional information about this type of clusters. And interesting that they can grow, behind the filament as well as before the filament. So this is not like a totally different structure from the inertial interception, I would say, or diffusion interception. So this type of clusters are collected by van der Waals forces, okay? Now, why, okay, I have many more, because I like them, like kind of a lot of clusters like that, very unusual. The efficiency is shown here. So the efficiency of the basic filter goes like that, and the efficiency of the filter with added supersonically blown fibers is going like that. So definitely the efficiency increases quite dramatically, and interesting that the lower concentration is, the better you are, okay? Just the opposite to the gut feeling. Now, let's skip over all this and let's consider like the main phenomena here. So this is essentially like a solution of like a flow pattern about a cylindrical collector, okay? This is a fiber, okay? So these are the streamlines. So you see that a collector essentially displaces the oncoming liquid more or less on the scale of like itself. So if your collector is, for example, an Electrospun nanofiber, which is like 500 nanometers, so it displaces, fluid to 500 nanometers. And when it goes to 500 nanometers, all the particles which are embedded there, passing by there, they are unaffected by van der Waals forces, because van der Waals forces act only not beyond 100 nanometers, okay? So that's the point. Therefore, when you have a collector which is less than 100 nanometers, displaces, liquid to less than 100 nanometers. So then van der Waals forces will begin to play a role and add to collection of particles. And it appears to be, it's a very effective collector. Now, okay, I'll skip over the details, and this is essentially a summary of what I told you about, like the van der Waals forces make tiny fibers, tinier than 100 nanometers, and you have a new filtration mechanism which adds to all the other ones and helps you to remove particulates. Now, let's take a look at the experiment we did, during COVID, because COVID is like exactly like. Okay, COVID essentially begins with some droplets, coming like from an affected human being, and inside there are viruses, okay? And it's not only COVID, it's all together, okay? Hepatitis C is also like a very good thing, to catch, through droplets. So then, it's easy to show that any droplet which is below 20 microns, and there is a lot of droplets like that, evaporates before it settles. So it means that if it contains, particulates like viruses, okay, like COVID viruses, okay, then these COVID viruses become airborne. So you have, and the COVID virus is exactly 100 nanometers, in size. So 100 nanometers in size, airborne particles are not stopped by any face mask, okay? This is just like a mirage to think that this face mask, stops anything of this type, okay? So, and we try to catch them using the van der Waals forces, number one, okay, and also adding electrical forces, number two. So how to add electrical forces to metallize nanofibers? How to metallize nanofibers? We developed, and I'll tell you later, the process. The process we use, to like metal plate nanofibers, but electroplating, makes fibers, thicker, and we don't want them to become too thick. So we take, our 50 nanometers nanofibers and sputter coat on them. So then we have, van der Waals active nanofibers with metal coating altogether below 100 nanometers. So then we can make the filter essentially like a part of an electrode and catch particles, by means of van der Waals and electrical forces. And we did this type of experiments, and okay, I have to skip over given the time. So these are the particles of the size of COVID viruses we used, and we showed that collection goes on the tiniest fibers, as I already told you. The electrical forces add to the van der Waals forces, and you can increase, 4 times the efficiency of interception of this type of particulates using a combination of van der Waals and electrical Coulombic forces. Okay, that's the main takeaway from this part. And the last part, for which I have 1 minute, right? I'll show you just in brief. So you can definitely electroplate nanofibers, okay? Then they become metallized and thicker, okay? So you lose van der Waals, but you still, have Coulombic interaction. And we did some experiments to see how electric forces remove, particulates, and they remove dramatically. So this is like the electroplating process I showed you. So this is the type of fibers we get already electroplated, and this is the experiment. So the membrane, which is an electrode, is standing here, and this is in this case it's carbon monoxide is passing by. So when voltage is off, it's passing by. The smoke essentially is passing through. Now, when voltage is on, the smoke does not pass through. So you stop it completely, and the observations we made show you that everything is intercepted here. So it looks like a liquid film appears, but essentially it's not like a liquid film. It's a deposited soot appears there. Okay, and we demonstrated this type of interception, with multiple particulates. I'm just skipping over all this. So these are examples of different particulates we removed, and we showed also that we can clean these fibers very easily. And in addition to that, the last thing I'll tell you before I'll stop on time is that when you have metallized fibers, so you also can use them as an incinerator. So you essentially use joule heating from a battery of 3 volts only to burn effectively, these, for example, viruses which are intercepted. And this is another issue because, face masks are checked, on their breathability, and you all have experience now with that, okay, when they are clean. And all of them in 20 minutes, do not pass this test anymore. So people, who wear them, for more than 20 minutes, they are essentially depriving themselves from many, important issues related to breathing. So given the time, I'll better stop here and I'll take your questions. Thank you for your attention.
Thank you, Alex, for a very, very interesting plenary talk. The discussion is now open. So,
very good presentation. I have a question. So have you measured the residual charges that could potentially remain in these nanofibers as a contributing effect to stop the particles? Or you think that is pure van der Waals?
No, yeah, we did experiments, we did experiments where fibers were without any metal coating, okay? Then you measure pure van der Waals. Then you add, metal coating, and you measure once again the interception. Then you have van der Waals plus Coulombic forces. And then you can compare, and you see that, van der Waals yields you this. Coulomb adds something else, okay? So that's how we distinguish. By the way, I didn't say here one additional thing. So when you operate with Coulombic forces, you expect your particles would be charged, okay? Because you essentially need, you know, a charged particle to be attracted to a charged filter. Now, some particles do have charge, and you, like the majority which come from fire, for example, from fire, like from smoke, they are charged, okay? So they are radicals, you can intercept them this way. But there are many others which are not charged. So then you have, and I have here multiple slides about that, a simple just section of like duct, you know, which is an ionizer. And this ionizer, which operates at several volts, provides you negative charges which are embedded, trapped by particles, okay? And then you have negatively charged particulates, whatever, even so they are neutral initially, okay? Which are removed to the positively charged filter. And in this sense, you know, like using actively powered filters from my point of view is much more effective than try to embed the so-called electrodes. You probably know that people are for the electrodes, how to embed charges in the filter forever, and they never stand, and in many cases they just don't work. And in this case, you do not depend on that. You know, the moment you turn on voltage, you have your electrodes. That's your electrode. Yeah.
Any more questions?
Thank you for a very insightful presentation. I have a physics question. So in the water droplet experiments, what is the mechanism exactly? I didn't really understand that when the water droplet hits the surface at like 2 meters per second, but then the jet of water leaves the surface at 3 times higher velocity. What causes that?
Or, yeah, that's hydrodynamic focusing. You probably heard about shape-charged jets or rocket-propelled grenades you read today every day in newspapers, okay? That's exactly the same mechanism. And you are familiar with that. You go with your kids, you know, to the seaside, and you begin playing like that. So you clap your palms, okay, and squeeze water to the kids, right? So this is the velocity of 1 meter per second, okay? And this is the velocity 10 meters per second. So that's exactly the mechanism. So you embed, you know, you embed kinetic energy this way and issue this kinetic energy through a tiny orifice, okay? So then you focus your kinetic energy and it goes, you know, very fast. And even so, there is a dissipation, obviously, after that in the filter. It's still, you know, insufficient, you know, to suppress this effect, and you have a higher outflow velocity than the inflow velocity. In that case, I showed you. However, you can make the filter thicker and thicker and thicker, and after all, dissipate everything. But do you allow yourself doing this? That's another question. Okay, so that's the mechanism. That's how it works. And these shape-charged jets, it's the same thing done with metal. So metal cavity collapses due to the explosive action, and squeezed, you know, ductile metal is squeezed and perforating tanks. Okay, that's how it works. Like, and this is exactly like a fluidic mechanism.
Yeah, we have one more question here, Asa.
Hi, thank you, Alexander, for that talk. Related question to the previous question. So, in that first example, you were looking at through thickness velocity. But what about the in-plane velocity? Because you've got this 2 meter per second volume of liquid, but there is, the matter's anisotropic, so you would also get velocities in plane, and potentially, do you see changes in like water volume?
No, this is absolutely impossible. In plane, it goes by the gradient essentially. Gradient in this direction is very high. Gradient in that direction is very low. So therefore, filtration in plane is much less than filtration out of plane. Okay, that's what you clearly see. You know, these images I showed you here. Let me come back for a second. I'm sorry. Going back.
We can maybe pick this up after the talk, maybe in the
it's here.
Coffee break.
Yeah, take a look. You see that all these jets coming down. They are practically coming down under the droplet. Okay, nothing is outflowing from here because the filtration gradient. That's what's important. dl is very high in this direction, very low in this direction. So most of the fluid goes straight forward this way. Even so, definitely, the channels are tortuous like that, okay? But tortuosity, yes, plays a role. But it goes tortuous this way, not tortuous that way.
Yeah, I've done some X-ray imaging. So this is small-scale imaging, and you see liquid in plane. So optically, you won't see it.
This is because of tortuosity. But when you are talking about out of plane, I understand on the scale of a droplet, not on the scale of tortuosity.
Let's thank the plenary speaker again.
Thank you.